السلام عليكم. لا تنسوا الاعجاب بالفيديو والاشتراك في القناة.
Hi, and welcome to our third lecture in
لا
aerodynamics.
تنسوا
Last time, we briefly covered the variables that most commonly appear in the study of aerodynamics and how these fluid characteristics lead to forces on an object. Today, we'll cover how distributions of these flow properties, specifically the pressure and shear, generate body forces on an object and the resulting moment. So, let's jump right in. In aerodynamics, we're generally concerned with the forces produced on a body traveling through air. As we all know by now, an object moving through a fluid feels force, which is like the motto of aerodynamics. So, let's draw our object in a flow, in this case an airfoil. The flow moves around the object, changes direction, and results in a net force on the object. From our fluid mechanics studies, we know that flow can be wildly complicated and difficult to understand. Things can be separated, turbulent, and impossible to calculate. However, one nice simplicity of fluid forcing is that it really can only come from two sources, regardless of how complicated the flow is. There are normal forces on the surface of an object. These are called the pressure forces. Typically, the force is distributed over the surface, which is why we talk about it in terms of a pressure, which is a force per unit area. And the other way to force a surface is through tangential forcing, which we call shear stress. Stress is also a force per unit area. Commonly, this is associated with the viscous force and the flow viscosity, mostly because it is the dominant shear term in the governing equations of fluid mechanics. Often in aerodynamics, the surfaces that the air passes over are complicated, and this makes the pressure and shear distributions over that surface also complicated. Take, for example, the pressure and shear distribution over an airfoil. These two distributions are the contributors to the lift and drag of the foil. The pressure distribution is capital P, and if we are thinking of surface pressure, then we consider it along the curve S, which represents the foil surface. Similarly, the shear stress is the Greek letter tau, also presented along the S curve. Here, I'd like to pause and consider this curve S, because it will pop up in aerodynamics a lot. You may be wondering, why make it a function of S, and not just X and Y, as we would with any other flow field? The coordinate S follows a curve, and can only represent a point on that curve. X and Y define the entire two-dimensional space, and can define any point on that plane. All of the points on S can be equally represented by X and Y. However, in aerodynamics we encounter a ton of complicated surfaces. Cylinders, spheres, airfoils, fuselages, yada yada. And for the most part, we care about the forces on the object, which happens at the surface where the air meets the object. As we'll see from the math in this video, it is more convenient to define the curve S and use that than to keep track of the X and Y coordinates of the surface. Okay, back to it. Pressure and shear both produce a net force on the object. Let's consider some simple examples of how the distribution results in a net force. Consider inviscid flow over a stationary cylinder. Inviscid here meaning we will primarily be concerned with the pressure distribution and will ignore viscosity. We can mark our X and Y axis as well as the S coordinate, which follows the cylinder surface. This is what the pressure distribution would look like, where it is large on the top and bottom of the cylinder and smaller in the front and back. Notice that the pressure distribution is the same when comparing the top and bottom as well as the front and back. But this means that there is no net force in the X and Y directions on our cylinder. Every pressure has an equal and opposite on the cylinder. No pressure difference means no net force. A quick historical note, this actually caused the famous D'Alembert's paradox. Early in our understanding of fluid mechanics, we didn't know about viscous forces. So everything we knew about fluid forcing came from pressure. D'Alembert noticed that, according to his equations, there should be absolutely no drag on the cylinder, like our